All right, strap in, everyone. Today we're diving headfirst into a world where quantum mechanics and AI collide.
Sounds intense.
It is kind of mind-blowing, actually. We're talking about variational quantum neural networks.
VQNNs. Catchy, right?
Definitely rolls off the tongue. And to guide us through this, well, we've got Jorgo Schneppat's essay.
VQNNs. Variational Quantum Neural Networks for Chi Revolution. Quite a title.
It is. But Schneppat really lays it all out, Helps us understand what makes these networks tick.
And why everyone's getting so excited.
Exactly. So, before we get lost in the quantum weeds, how about a quick level set? Quantum computing, everyone talks about it, but what's the big deal?
It's more than just talk. It's a whole different ballgame. Imagine this. Classical computers use bits, right? Like a light switch, on or off, 0 or 1.
Got it, the basics.
But quantum computers, they use qubits. Now, these can be in both states at the same time, like a spinning coin before it lands.
Whoa, hold on. They're both 0 and 1 at the same time.
Precisely. It's called superposition. And it's what lets these quantum computers explore tons of possibilities all at once.
Okay, my brain's starting to hurt. But I guess that's why they're so much faster than our regular computers.
For certain problems, yeah, exponentially faster. And then there's entanglement. Now, this is where qubits get all connected.
Connected how?
Well, you change one and the other changes instantly. Doesn't matter how far apart they are. Even Schneppat quotes Einstein calling it spooky action at a distance.
Okay, yeah, spooky is one word for it. I'm definitely seeing the appeal, though. But Schneppat isn't just geeking out about quantum computers, right? He's talking about using them for AI.
You got it. VQNNs are all about marrying quantum computing with AI. It's a hybrid approach using the strengths of both. And Schneppat emphasizes this because, well, we're still in the early stages with quantum computers.
So no quantum laptops replacing our Macs anytime soon.
Not quite. It's more like a tag team. VQNNs use the quantum side for those really heavy calculations and the classical side to keep things organized and under control.
Gotcha. So how does this quantum classical dream team actually work? What are the moving parts here?
All right, picture this. A VQNN has a quantum circuit. It's like a sequence of operations, but on these qubits, the catch. These circuits can be adjusted, like fine-tuning a high-tech machine.
Schneppat called them quantum Lego blocks, which I kind of love.
Perfect analogy. We're building these circuits and then tweaking them to do specific jobs, but the tweaking, the optimization, that happens on the classical side.
So we've got our quantum circuit doing its quantum thing, and then classical algorithms are basically playing puppeteer.
Exactly. And those classical algorithms, they learn from data. We feed data into the quantum circuit, see what comes out, and then use that feedback to adjust those settings. It's a learning process, very iterative.
Okay, training a quantum computer, got it. But speaking of training, how does a VQNN actually learn? What's the magic behind the curtain?
It's called gradient-based optimization. Think of it like this. We're trying to find the perfect settings for our VQNN to do its job well. And the gradient part, well, it tells us which way to tweak those settings to get better and better.
Makes sense. But Schneppat also mentions these barren plateaus. What are those all about?
That's one of the puzzles researchers are working on. Imagine trying to find the lowest point in a huge flat field. Hard to know which way to go, right? Because the gradient, our guide, is basically 0.
So the VQNN gets lost.
In a way, yeah. The learning process hits a wall. But don't worry, Schneppat highlights that researchers are coming up with clever solutions, like carefully designing those quantum circuits or giving the VQNN a good starting point.
Glad to hear it. Sounds like we're still ironing out the kinks, but making progress. Okay, but enough theory. What about real-world stuff? What can we actually DO with these VQNNs?
Now that's where things get exciting. Buckle up, Jorgo Schnepppat. He really paints this picture of what VQNNs could do. And it's a big picture.
Give me the highlights.
Well, we're talking revolutionizing machine learning, optimizing all these complex systems, personalized medicine, AI designing materials, even like smarter logistics, financial decisions, you name it. It's a huge, wide open field.
Okay, color me intrigued. Personalized medicine, though, that really caught my ear. How would VQNNs actually shake things up in healthcare?
Imagine going to the doctor, right? And instead of getting some generic treatment, they use a VQNN. It analyzes your whole medical history, your genes, even like lifestyle stuff, and it creates a plan just for you.
So it's not about just finding new treatments, but figuring out how those treatments will work with each person's well, unique biology.
Exactly. And Shemeppat even talks about material science, like designing new materials that are super strong or maybe even superconducting. VQNNs, they could help us understand how atoms and molecules interact, on a really deep level.
So it's like having a quantum microscope to see the tiniest building blocks of stuff. But okay, let's be real. There have got to be some challenges.
Yeah.
Shemeppat mentions those too, right?
Oh, for sure. One of the big ones. We need better quantum computers, like way more powerful, less prone to errors. Schnepptat points that out pretty clearly. And we also need to develop better algorithms, the instructions for these VQNNs.
We need better hardware, Andy, better software. Sounds like a tall order.
It is. But here's the thing. The progress in this field. It's moving crazy fast. Every year we see these breakthroughs in quantum hardware and with the algorithms. It's pretty amazing.
That's good news. Makes it feel less like science fiction, more like, well, the future is coming.
And it's not just about getting to that future. The journey itself, it's fascinating. Schnepphat really emphasizes that. Like, each step we take, it gets us closer to understanding how quantum mechanics and AI work together. It's profound.
Speaking of profound, there was this question Schnepphat asks at the end of his essay. Really got me thinking.
Yeah, he asks, could VQNNs be the key to solving some of humanity's biggest problems?
That's a big question. It's like he's asking us to look beyond all the tech stuff and consider what this could really mean for the world.
He is. It's not about faster computers. It's about using this technology to tackle global issues. Climate change, poverty, diseases.
Wow, that's a lot to take in. I guess that's what happens when you're dealing with a technology this powerful, right?
Yeah.
It makes you think about the big picture.
It does, and it reminds us that technology is just a tool. What matters is how we use it. What problems do we choose to solve? What values are we focusing on? Those are the questions we need to be asking.
You're right. Well, we've covered a lot of ground today, from the ABCs of quantum computing all the way to the potential of VQNNs. But I'm sure our listeners have more questions.
Definitely. There's always more to learn.
Welcome back. We've been exploring VQNNs with Yorgo Schnepphat as our guide. It's been quite a ride.
It has. All those possibilities. Medicine, materials, solving those wicked problems. But also the reality, we need better quantum computers, right?
And that brings up a question. How long until we see VQNNs actually making a difference? Are we talking years, decades, or am I getting a quantum phone next week?
Well, Schnepphat doesn't give a timeline, but he does talk about how fast things are moving. Quantum phones next week? Probably not, but real-world uses in specific areas. Maybe not so far off.
So no quantum selfies for now. Bummer. But what about things like drug discovery, material science? Those seem ready for a quantum boost.
Absolutely. Even small improvements there could be huge. Imagine designing a new drug way faster than we do now. That would change everything.
It's like Schnepphat's essay is a glimpse into a future where problems that seemed impossible, well, they become possible. But there's something else I've been thinking about. We're combining quantum mechanics and AI, two incredibly powerful things. Are there any downsides? Anything we should be worried about?
That's a great point, and one we need to think about carefully. Schnepphat focuses on the positive side of VQNNs, but any powerful tool can be used in the wrong way, right?
So it's not just the technical hurdles, it's making sure this technology is used for good.
Exactly. We need to be thinking about ethics, about biases in the data we use to train these VQNNs, about how this all affects society as a whole.
It's a lot to consider, but important to talk about it now while things are still developing. We have a chance to shape how this technology is used, make sure it benefits everyone.
I agree. Schnepphat's essay really shows us that we're entering a new era, one where quantum mechanics and AI, well, they're becoming more and more intertwined.
And as we head into this uncharted territory, it's up to all of us, scientists, policymakers, everyone to make sure this technology is used wisely for the good of humanity, for the planet.
Absolutely. Big thanks to Euro Schnepphat for that insightful essay. It was a perfect guide for our deep dive into the world of VQNNs.
And to our listeners, keep exploring. Keep asking those questions. The future is full of quantum possibilities, so stay curious.